Okay, so this video is about the first video on solving differential equations, and actually this technique we're going to use today is possibly a review for a number of you, depending on where you learned your integral calculus. You may have had a little small section on solving differential equations. So this is an analytical technique called separation of variables. So, and of course, not every differential equation can be solved using this method, but we're going to look at some today that are what are called separable. Separable? Yeah, separable. So, what does it mean to be a solution? So, as you see written here, a solution to a differential equation is a function that can be substituted into the differential equation, and it satisfies or makes the equation true for all values. So, remember, a differential equation is an equation with derivatives in it. So, here's an example of differential equation. I'm going to just take that out because I really prefer the Leibniz notation anyway. So let's do this. So remember, what we're saying here is that the derivative is set equal to some function involving y and t. And it could be just y or just t or a combination of y and t. And so the solution we're looking for is this y of t. What is the function? So what is y of t that will make this equation true? So some function of t. Okay, so just for example, if we have dy dt, for example, a very simple differential equation, dy dt equals y. So this is basically saying the derivative of y is the same as y. So we're looking for a equation of y, because remember we're saying y is some function of t. So we're going to come up with some equation like y sub 1 of t. So this is a potential solution we're saying. So maybe that might be a solution. And here's another potential solution that we're just going to check out. So there's two functions of t that we could possibly try to sub in here and see if it works. So when we sub in, that means we're going to have to replace dy dt with the derivative of my y1 and my y2. So let's deal with the y1 first. So we're going to check y1. So if we plug into this equation, we get now the derivative, so that would be y1, that would be the prime, y1 prime, and that would be equal to y, which is just 3et. That's the question. Is that true or not? So what is the derivative of y1? Well, the derivative of y1 is just 3et, isn't it? So we find out that it is true, that the two of them are equal to each other. Now, if we check the second one, let's check y sub 2 of t. That's equal to sine t. So now when we plug into this dy dt is equal to y, let's see if it gives us a true equation. So the derivative of y sub 2, would be cosine of y, and of course y is just sine of y. I'm sorry, cosine of t, my bad. Cosine of t and sine of t. Now, is that a true equation? No, it is not. So that means this is not a solution. Not a solution. And this one is a solution. Okay. So here's just to get you a little involved here. So let's say that we have another one, dy dt is equal to y squared minus 1 over t squared plus 2t. So a little bit more complicated differential equation. So what we're going to say is I'm going to give you three possible solutions. So let's try y sub 1 of t is equal to 1 plus t. And we'll say y sub 2 of t is equal to 1 plus 2t. And y sub 3 of t is equal to 1. So I'm suggesting these three are potential solutions to this differential equation. And so what your job is to check and see if they are. So if you want to do these things the right way, I would pause the video right now if I was you, and I would try just plugging those into the equation and see if they work. Okay? So I'm assuming that you've paused the video, tried it out, and now you're back. And so we're going to go ahead and I'm going to do these for you. So let's see. As we test these, dy dt is equal to, whoops. So we're going to take, for example, this one. So we're going to take y sub 1 of t. We're going to check it. Okay, so the derivative of that, what's the derivative of 1 plus t with respect to t would just be 1, right? So then if we plug 1 plus t in for y, we get over here 1 plus t squared minus 1 over t squared plus 2t. Right? So let's see if that's true. 1 is equal, now, 1 plus t squared, that'd be 1 plus 2t plus t squared minus 1 all over t squared plus 2t. Now, 1 plus negative 1 is 0, so what we have is 1 is equal to 2t plus t squared over t squared plus 2t. And the question is, are those two equal to each other? And sure enough, they are. As long as t is not 0. So in this case, we would say it works, except for t can't be equal to 0. But it works everywhere else. We'll talk about that in a minute. Okay, now let's check, check y sub 2 of t, which we said was 1 plus 2t. So once again, if we grab that equation, dy dt, the derivative of that would be just 2. And again, if we plug in these numbers, so we're going to plug in 1 plus 2t squared minus 1, and that's going to be over t squared plus 2t. 2 is equal to, now when I multiply that out, I get 1 plus 4t plus 4t squared minus 1 all over t squared plus 2t. And we get 2 is equal to the 1 and the negative 1 add up to 0. And we get 4t plus 4t squared over 2t plus t squared. And the question is that twice as big as that? And the answer is no. Almost, if we would have had 2 there, it would have worked, but we don't. So this is not a solution. All right, so then if we go down to the last one, I forgot what it was, just 1. Oh, that's a simple one. So we're going to check for y sub 3 of t, which is equal to 1. So the derivative of that is, of course, going to be 0. And then we plug 1 in everywhere we see y into my original equation. So that would be 0 on top. And not that I need to keep going because we see it works, but t squared plus 2t on the bottom. And sure enough, 0 divided by anything is 0. So this does work. So it is a solution. Okay, so hopefully you got something like that. So I think we'll stop here. This will be a shorter video that just talks about what it means to be a solution to differential equation. And then the next video will be on actually solving a couple of differential equations.